So we are given a rectangular box with a square base and an open top is constructed from two different grades of cardboard. The material for the sides costs 1 cent per square meter, and the material for the base costs 4 cents per square meter. If the cost of the materials of the box is limited to $1.08, find the dimensions of the box that maximizes the volume of the box. So we're given that the box with the open top is going to have a square base. So we'll let X, right, represent the length of one side of the base. Right? So the area of the base is X squared. Okay? And it's got an open top, right? I think we did a similar problem like this yesterday. Okay? This is one side of the box with the open top. So each side of the box is going to have a width of X and a height of H. Okay. So H is the height of the box. Okay. Now, the cardboard that's used to make the sides of the box, right, costs 1 cent per square meter. Okay. So 1 cent in dollars is 1/100th of a dollar, right? And the cost of the cardboard for the bottom of the box, the base of the box, costs 4 cents per square meter, right? Which is 4/100ths of a dollar. Okay. And our budget constraint, right, is that the cost of materials of the box is limited to $1.08. So $1.08 is the same as 108 cents. It's important that we get our units correct, right, in solving this problem. In solving this problem, we either got to have our dollar or our monetary denomination in dollars or in cents, right? We got to have one or the other. Okay. All right. So we want to maximize the volume, right? So in this problem, we're going to maximize the volume, which is equal to, okay, with, right, length times height, right? And so we went through this yesterday in another problem. And so the volume is X squared times H, okay? All right, just to remind you, volume is length times length, or width times height. Okay. So length times length is X times X, and height is H. So we got to maximize that volume subject to a budget constraint. Okay. Well, the area of the bottom of the box, or the base, is X squared meters. And each square meter costs 4 cents. So the total cost of the cardboard for the bottom of the box, the base of the box, is 4 times X squared. The area of the bottom of the box is X squared meters. The cost of the cardboard for the bottom of the box is 4 cents per square meter. And so the total cost of the cardboard for the bottom of the box is 4 times X squared. Okay. The area of each side of the box is X times H. And there are 4 sides to the box. So the total area of the 4 sides of the box is 4 times X times H. You notice I left a space there. And each square meter, the side of the box costs 1 cent. So the total cost of the cardboard for the 4 sides of the box is 1 cent times 4xh. This is the total area of the 4 sides of the box, and it costs 1 cent per square meter for the cardboard for the sides of the box. Okay. So the cost of the bottom of the box plus the cost of the sides of the box has to equal $1.08 or 108 cents. Right? So this is the cost of the base, and this is the cost of the 4 sides, and this is the total cost for the entire box. You got to construct that box using exactly $1.08 in materials. Okay. Well, this is our budget constraint, right, in terms of X and H, and we can solve for H. So when we solve for H, we have 4, right? 1 times 4 times X times H is 4xh. Then I subtract from both sides, it's 4x squared. Actually, I did one other step. Well, no, we can save it. We'll keep going. So now I divide both sides by 4x. And h is equal to 108 minus 4x squared over 4x. Okay. Now, when I worked this problem in my office, what I did first is divide both sides by 4, because 108 is divisible by 4. And so I can simplify what h is equal to by dividing 4 into 108 and 4 into 4. And I get h is equal to 27 minus x squared over x. Each of these coefficients, right? Each of these coefficients up here is divisible by 4. Right? So you divide by, simplify the problem and solve for h. Okay. So whatever the width, right, the length of one side of the base is, okay, this is what h has to equal, okay, based upon this budget constraint, okay, so that we maintain our materials cost at $1.08 total for the box, okay. All right. So we're maximizing the volume, x squared times h. Well, now if we substitute for h from our budget constraint, our volume is a function of x only. So now we're going to maximize f of x, which is equal to x squared times h, where h is equal to 27 minus x squared over x. And our function here, right, you know x has to be greater than 0. Right? You can't have a width or length of one side of the box that's 0 or negative. Right? The length has to be positive. And so now we simplify. X squared divided by x is just x, right? So we can cancel this x and one of these x's. And we're left with x times 27 minus x squared. And when we distribute the x, we have 27x minus x cubed. So that is the function we have to maximize. So we look for the critical numbers. So f prime of x is equal to 27 minus 3x squared. And now we set the first derivative equal to 0. And solve for x. And when we move, we add 3x squared to both sides and switch the two sides. We get 3x squared is equal to 27. Divide both sides by 3. You get x squared is equal to 9. Take the square root of both sides. You get x is equal to negative 3. You get x is equal to plus 3. Well, minus 3, right, is less than 0. So that critical number doesn't work. And we're left with x equals 3. It's the only critical number for this problem. Okay. So it seems the optimal length of each side of the base, right, the bottom of the box is 3 meters. And then we can get the height from the formula for h. Okay. But we got to see if we got a minimum or a maximum. So we can do, right, f of x is a third degree polynomial, right? It's differentiable. Okay. And so we do the second derivative test. Differentiate the first derivative, derivative 27, 0. Your derivative minus 3x squared is minus 6x. And when we put in 3 in for x, okay, we have the second derivative at x equals 3 is equal to negative 18, which is less than 0. So the concavity is negative, right? The graph is concave down at x equals 3. So we have a local slash absolute maximum. So x equals 3, okay, maximizes, okay, the volume, right, for our box. And it maintains the cost at $1.08. Okay. So x equals 3. equals 3 meters. Right? I guess I used the word length instead of width. Okay, so I'll stick with that. And then the height h, when you plug in, I guess I erased the formula. Okay. When you plug in for x and h, you get h is equal to 6 meters. So let's do a check to see if our total cost in this box is going to be $1.08 or 108 cents, right? So the area of the base at the bottom is x squared, right? Here's our formula right here with the budget constraint. So x squared is equal to 3 squared, right? So the base of the box, right, is 9 square meters. The area of each side of the box is x times h, right? And there are 4 sides, and x times h is 18, right? 3 times 6. And now when you do the arithmetic, 4 times 3 squared is 36, and 4 times 3 times 6 is 72? Yep. And 36 plus 72 is equal to 108 cents, which is equal to $1.08. So those are the optimal dimensions, okay, that maximizes the volume of the box and keeps the cost of the box, producing the box at $1.08. Cost of materials at $1.08. Okay. Did you work this one in advance? Did you get the same thing? Okay. Cool. All right. Any questions on that? All right, so that ends the optimization handout. And so we will I'll get that homework released today. It'll be due Monday night. All right. So now let's talk about anti-differentiation. And anti-differentiation, right, is our introduction, right? It's our doorway into another area of calculus called differential calculus, or not differential, integral calculus. We've been doing differentiation, okay? So we've been dealing with differential calculus. And now in chapter 5, right, that deals with integral calculus. All right, so, you know, we have a function f of x that's differentiable, right? And given a function f of x that's differentiable, right, we can differentiate and get its first derivative, and then differentiate the first derivative and get its second derivative, and so forth, right? Anti, right? The prefix anti, right, kind of means what? Against, okay? Or go in reverse. And so anti-differentiation. So differentiation is we go from f of x to f prime of x to f double prime of x, right? That's differentiation. Anti-differentiation, in essence, is you're going from the second derivative to the first derivative, and from the first derivative back to f of x. Okay. And what comes before f of x is big F of x. And anti-differentiation is, in essence, is going from little f of x to big F of x. Okay. So we've given f of x, we know how to find its derivatives, right? It's higher order derivatives. But we're interested in giving f of x what function, right? What function big F of x has a derivative equal to little f of x. Okay. So we're asking a different question. So definition at the top of page 1. Okay. A function big F is called an antiderivative of little f if big F prime of x, right, the derivative of big F is equal to little f. So given a function little f, we're interested in a function big F whose derivative is equal to little f. How do we find that function? Okay. Whose derivative is equal to little f. So if you look at the example down below our definition, okay, we know that 3x squared is the derivative of x cubed. Right? The derivative of x cubed, right, using the power rule, is equal to 3x squared. So little f of x is equal to 3x squared. Then a function whose derivative is equal to little f of x, function big F of x, whose derivative is equal to little f of x, is x cubed. If the derivative of x cubed is equal to 3x squared, then we say the antiderivative and antiderivative of 3x squared is x cubed. Because the derivative of x cubed is equal to 3x squared. And so if I differentiate big F, I have the derivative of big F prime of x, is equal to 3x squared, which is equal to little f. Okay. So the derivative of x cubed with respect to x is equal to 3x squared. And so an antiderivative of 3x squared is x cubed, because the derivative of x cubed is equal to 3x squared. Okay. That's kind of what the definition is saying. Okay. And so I demonstrate that here, right? If big F of x is equal to x cubed, then the derivative, right, of big F prime of x is equal to 3x squared. By the rules of differentiation, by the power rule. But there are other functions, right, that are antiderivatives of 3x squared. Right? Big G of x, right, equal to x cubed plus the constant 100. When you differentiate that, right, derivative of x cubed is 3x squared, derivative of the constant is 0. So G of x, big G of x, is also an antiderivative of 3x squared. And the same is true for big H of x, right? It's equal to x cubed plus pi, right? Pi is the number 3.141. And when you differentiate big H of x, right, you get big H prime of x is equal to 3x squared. So big H of x is also an antiderivative of 3x squared. Well, it turns out, right, all the antiderivatives of 3x squared differ by a constant. You notice that the difference between big F, big G, and big H, right, they all differ by a constant. Okay? They all have x cubed, right? But the constant is different. Okay? So, in theorem 4.91, if big F is an antiderivative of little f, then the most general antiderivative of little f is big F of x plus c. Okay. Because all the antiderivatives for little f will just differ by some constant c. Okay. Get the basic idea? Yeah? No? If you don't understand, say something. Right. So in the exercise down below, okay, find the general antiderivative of the function. Okay. So all the antiderivatives of little f of x are only going to differ by a constant c. Okay. And so we're going to find the general antiderivative of the function. So if little f of x is equal to 2x plus e to the x minus sine x plus secant squared x minus 1 over x. Okay. Now that's a lot, okay? But there is some function, big F of x, whose derivative is equal to little f of x. And so we're going to find that antiderivative and write out the most general antiderivative for little f of x. Now in doing this, we're going to use the knowledge that we have with differentiation. So the derivative, starting with the first term 2x, the derivative of x squared with respect to x, you know, by the power rule of differentiation, is equal to 2x, right? So 2x, or excuse me, so x squared is an antiderivative of 2x. X squared is an antiderivative of 2x. This derivative of x squared is 2x. So in our first term for big F of x is x squared. The derivative of what is equal to e to the x? E to the x, right? So the derivative of e to the x is e to the x. So e to the x is an antiderivative of e to the x. And all antiderivatives of e to the x differ only by constant c. Okay. So in the second term of big F of x, we put e to the x. The derivative of what is equal to minus sine x? Cosine x, right? So the derivative with respect to x of cosine x is equal to minus sine x. So cosine x is an antiderivative of minus sine x. So what's our third term? Yeah, it's going to be plus cosine x, right? Because the derivative of cosine is x minus sine x. The derivative of what is equal to secant squared? Tangent x. So the derivative of tangent x with respect to x is equal to secant squared x. So tangent x is an antiderivative of secant squared x. The derivative of what is equal to 1 over x? Natural log of x. So the derivative of the natural log of x with respect to x is equal to 1 over x. So the natural log of x is an antiderivative of 1 over x. And so we have minus the natural log of x. And now all the antiderivatives of little f of x differ by a constant c. So to write the most general antiderivative of little f, we add the arbitrary constant c. And now you see when you differentiate big F of x, derivative of x squared is 2x, derivative of e to the x is e to the x, derivative of cosine x is minus sine x, derivative of tangent x is secant squared x, derivative of minus log x is minus 1 over x, and the derivative of a constant is always 0. Some of you forgot that on the ladder problem. Right? The ladder was 10 feet long, and you had x squared plus y squared equals 10 squared. Derivative of 100 is 0. All right. Any questions? So you get the idea. Okay. Given little f of x, instead of differentiate, right? We can differentiate little f of x and get f prime of little f prime of x, right? Instead of finding little f of x's derivative, we're finding a function whose derivative is little f of x. Okay. All right. Any questions on that?
How difficult would it be to find what that constant is?
Well, you see, in the examples above, right, we said, right, we gave 3 examples where there's an infinite number, right, because the real number line has an infinite number of numbers, right? So there's an infinite number of antiderivatives, right, of little of 3x squared. Okay. The time when we can calculate what c is, we got to have one more piece of information, okay, for the problem, and we'll do that. It's called an initial value problem, where we're told little f of x is, well, f of 5 is equal to 10. Little f of 5 is equal to 10, and then with that information, okay, we can plug in, okay, and calculate what c is. Okay. Okay. So you got to have more information to get right to get the specific value of c. All right. You ask good questions, Steve. Okay. All right. So now let's talk about the indefinite integrals, okay, which is finding the general antiderivative of a function little f of x. But we have symbolism in mathematics for finding to indicate we're going to find the antiderivative of f of x. So given a function little f, okay, the indefinite integral. Now we're going to be studying in future definite integrals, right? So there's a difference between indefinite and definite integrals. So given a function little f, the indefinite integral little f is denoted with this symbolism, okay? And this is called the antiderivative or the integral symbol, okay? And it looks like a stretched out summation sign, and there's a reason for that, okay? Which we'll get into in future. So this symbolism tells us that we're going to perform the act of anti-differentiation on the function little f of x, okay? And the dx means we're going to find the antiderivative of little f of x with respect to the variable x, okay? That might sound unnecessary, but it is necessary when you do multivariate calculus, right? Where little f can be a function of several variables. Okay? It's important to indicate which variable you're going to be finding the antiderivative with respect to. Okay? So this symbolism, right, represents the most general antiderivative, little f, right, which we know is represented by big F of x plus the arbitrary constant c. Okay. Little f of x is called the integrand in the indefinite integral, okay, and the variable x, right, is called the variable of integration. So we won't say in words, right, define the antiderivative of a function little f of x, right? We'll use this symbolism. That symbolism, it tells us to perform the act of anti-differentiation. So just as there are rules of differentiation, there are rules of integration, right? So-called shortcuts. Okay? And so we will go through some of those today. The first one is the indefinite integral of a constant. And so k is just some real number from the real number line. Okay? And so the antiderivative of k with respect to x is equal to kx plus c. So in this first example, right, k is equal to 12. And so the antiderivative of 12 with respect to x is equal to 12 times x plus c. Right? That's the most general antiderivative. Okay. Now, how do you think we check to see if we got the right antiderivative or not? Take the derivative of the antiderivative, the right hand side, right? And so when you do your check, differentiate the right hand side, right, using the rules of differentiation. And the derivative of 12x with respect to x is 12. The derivative of a constant is always 0. And 12 plus 0 is 0. Okay. So when you differentiate your answer, you better end up with the integrand, okay, or you did something wrong. Okay. So this is the answer to that. The antiderivative of pi with respect to x, okay, same thing. Pi is just a constant, 3.141. So the antiderivative of the constant pi with respect to x is pi x plus c. And again, okay, you differentiate the answer with respect to x, and you end up with pi. Right? The antiderivative of 0 with respect to x. What's that equal to? Yeah, very good, Alex. C, right? Plug in, right? This is 0 times x plus c, and 0 times x is 0. And so the antiderivative of 0 is just the constant c. And the derivative of the constant c, right, is equal to the integrand 0. Antiderivative dx.
Zero. X plus C.
Who said that?
So what?
Was it-
She said it first.
Who said it first? Yep, x plus c. Because this is actually, there's the invisible 1 in front of the dx. Okay? If there's nothing there, it's the invisible 1. And so that antiderivative, right, is 1 times x plus c, which is x plus c. Okay. And the derivative of x, you know, is 1. Derivative of c is 0. Okay. Those are the kinds of questions like antiderivative 0 and the antiderivative dx are the kinds of things that would show up on the test just to see if you're paying attention. Okay. Alright, so you flip over to page 3. We have the power rule, right, of antidifferentiation. So we have the power rule of differentiation. Now we have the power rule of antidifferentiation. And you know when we differentiate a function, right, we have f of x is equal to x to the n. And we differentiate that by the power rule, we bring the n down from x, and then we subtract 1 from the exponent, right? Well, now we're finding the antiderivative of x to the n. And instead of subtracting 1 from the exponent, we add, and then we divide that new exponent, then we divide x to the n plus 1 by that new exponent, and then we add arbitrary constant c. And this denominator, n plus 1, right, it can be pulled out in front of the x to the n plus 1 and written as 1 over times n plus 1. Okay. So, just so you see that this makes sense, the derivative with respect to x of 1 over n plus 1 times x to the n plus 1 plus c. When you differentiate this first term by the power rule differentiation, you bring the n plus 1 down in front of the x, and then you subtract 1 from the exponent. You have n plus 1 over n plus 1 times x to the n, right? N plus 1 minus 1 is n, and the derivative plus c is 0. And n plus 1's cancel, and we're left with x to the n. Okay. So 1 over n plus 1 times x to the n plus 1 plus c is the most general antiderivative of x to the n. Yes, ma'am.
I missed it when you said this. That 1 right there is just coming from the x to the n plus 1. That 1 is just coming from in front of the 1 x to the
Yeah.
plus 1. Okay.
So x, right? So we have the quotient x to the n plus 1 over n plus 1.
Mhm.
Okay? And this can be written as a product of two quotients, right?
Mhm.
Okay, when you multiply two quotients, right, you just multiply straight across. And so then this is equal to 1 over n plus 1 times x to the n plus 1. Okay. So sometimes when you're finding an antiderivative using the power rule, right, of antidifferentiation, sometimes it's easier to do it this way, and sometimes it's easier to write it that way. Right? So let's look at the examples. Okay. Oh, now this doesn't work for n equals minus 1, obviously, right? Because when you put in minus 1 for n here, you have minus 1 plus 1, which is 0, and you can't divide by 0. Okay. So we're gonna find the antiderivative of x squared, right? And you'll notice from the formula, right, n is equal to 2 in this case. So add 1 to the exponent, divide by the new exponent, and then add the arbitrary constant c. And this is equal to 1/3 times x cubed plus c. And to do check, you differentiate your answer with respect to x. So using the power rule differentiation, right, you bring the 3 down from the x and subtract 1 from the exponent. Well, 1/3 times 3 is 1. And when you subtract 1 from the exponent, you have x squared, and the derivative of the constant c is 0. And so, derivative of our answer equals the integrand. So we have the right antiderivative. The next example.
Professor?
Yes, ma'am. Oh, got 2 hands up.
So is this a situation where we wouldn't simplify? Like we don't want to put x to the 3rd over 3 and we want to separate it out?
I mean, it just
It doesn't
depends
matter.
upon, yeah, if you wrote your answer as x cubed over 3, I'm fine with that. Yeah. Yeah. We're just pointing out that there's 2 different ways of writing that. They're equivalent. Yeah. All right. Which one to use? Right, whatever's the more convenient. Okay. All right, in the next one we have 1 over x to the 7th. The antiderivative 1 over x to the 7th with respect to x. So do you think that in finding this antiderivative, we add 1 to the exponent 7 and get 8, and then divide by 8? Yeah. The head's shaking no. I'm glad to see that. Yeah. Do we have some work? Do we got to change this? Yeah. How do we have to rewrite this before we can find the antiderivatives, right? And so how do we rewrite? Remember, this is called the integrand. How do we rewrite the integrand? What? X to the negative 7? Yep, that's correct. Right? 1 over x to the plus 7 is equal to x to the minus 7. Okay. And now you can use the power rule, right? So n is equal to minus 7 in this case. And so you add 1 to the exponent, you get minus 6, and you can divide by minus 6 plus c. Okay. Stop right there if you want, okay? Unless you're solving some kind of problem and you want to rewrite it to make the math easier, right? But this is also equal to minus 1/6 times x to the minus 6 plus c. And if you wanted to, you could write x to the minus 6 as 1 over x to the plus 6, right? So on the exam, just like, remembering the exam, was it 1, where you had to, well, both on exam 1 and exam 2, and even exam 3, right, you had to find derivatives of functions, and you were told you don't have to simplify. So you'll have a section where you got to find a bunch of antiderivatives, and you'll be told you don't have to simplify. Okay? But on the other hand, if you're solving some kind of problem, it might behoove you, right, to simplify, to make your life easier. Okay? All right. Man, we're running out of time. So we have, do it over here, the antiderivative of the square root of x. So before we find this antiderivative, what do we have to do?
Rewrite it.
Rewrite the integrand, right? And the rewrite the integrand is what?
Still 1/2.
Yeah, x to the 1/2. And now, this is the fun part, right? You add 1 to the exponent. 1/2 plus 1 is 3/2. And then you divide by 3/2. And then you add the arbitrary constant c. Now I may require you to simplify the don't divide by fractions, right? So 1 over 3/2 is equal to what?
Multiplying by 2/3.
It's 2/3, right? And so when they're fractional, right, coefficients, when you're dividing by fraction, I require you to flip it, okay, because this, I don't like that, right, divide by 3/2, right, multiply by 2/3. So that is the indefinite integral, right, of a constant and the power rule. Okay? And so we'll do more rules tomorrow. There'll be a second half to this handout. So let me get attendance, and then we'll call it a day.